my name is Thomas.
Hi, and I'm Brandy. Today we will be presenting you with our solar thermal chicken coop heater. So initially, this is a closed loop system. It has the solar loop on one end that contributes to the radiation loop on the other end. This project was originated by the idea of your infrared heaters being unsafe for the chicken coop, causing potential fires, electricity problems, and it could be harmful to the chickens if those events were to take place. So, in order to find a safer way to heat the coop on the cold winter days, we decided to conduct a closed loop radiant heating system that would run through the floor of the chicken coop in order to provide a constant heat for the chickens and to ensure that they were warm throughout the winter. To start, we evaluated the coop and we did heat loss calculations to figure out how much energy would need to be supplied to the coop based upon the building materials that are used to build it. With those calculations, we have conducted 8,853 BTUs per hour that were required to heat up the coop with an outside temperature of around 45 degrees and heating the coop internal temperature from about 40 degrees to 60 degrees. In the closed loop system, we have 3 solar thermal panels that are lined up here. The cold water comes into the end, and then the warm water will run out and it will go into a copper coil heat exchanger that is inside the 55-gallon drum. Then, after it removes from the copper coil, it'll return back to the solar thermal and it will be recirculated through a circulation pump. The circulation pump is then powered by a small solar thermal panel that is powered by solar radiation as well. With the pump being powered by solar radiation, it has the opportunity to alleviate the use of a controller. This indicates that when the sun is out and the water is being heated in the solar thermal panels, this indicates that when the water is being heated, it's also being circulated. So again, there is no need for a controller.
And here we have the closed loop system that is going into the coop itself. Although we have coolers right here, it was a save money on supplies. It first starts off as the inlet, comes in right here. It is just at the surface of the water to keep it to take the warmest water there is possible, because the warm water rises, and it flows through this pipe right here through another circulation pump that is also powered. So when measurements were taken through the coolers, these coolers represent the coop system. And we used coolers to ensure that the project was completed throughout the duration of the time due to unforeseen circumstances, due to parts and labor. And it goes through both coolers, and measurements were taken through both of these pieces of tape right here to ensure that there is the least amount of heat escaping from the coolers itself. Finally, the pipes run through back into the tank and head it into the tank overall, heating up again and starting the system over.
Through the use of all of the measurements, as you can tell, it's a pretty gloomy day today, and with the use of the solar thermal panels, it takes a lot of solar radiation to power them alone. And through the data that we collected, the temperatures from the inlet to the copper coil, the outlet to the copper coil, and then the measurements from the coolers, we were able to establish a high point of 1831.84 BTUs per hour that was produced by this system. And considering that our requirement was about 8,853 BTUs per hour, we can conclude that this system would not properly heat the coop for the chickens to be warm throughout the winter. One thing that we changed that we were not expecting from the original project design was the solar PV panel that powers the circulation pump. That was an addition at the end, again to alleviate the use of a controller, and we figured that it would be more environmental friendly that way. Lastly, the questions that we were asked based upon this project were, the first one, did you measure the temperature of water heated by the solar panel? As mentioned before, we did take measurements at the inlet, the outlet of the coil, and also into the coolers, which represent the coop, and we did that using a temperature gun, and we did that in 30-minute intervals from the time that the solar panels were turned on, and then we took measurements again at 30-minute intervals.
Another question that was asked by our advisor was, what was the biggest thing you learned from conducting this project? And the project taught us how important solar radiation is from the sun is in order to receive any heat gain from the thermal panels itself. The days that the data was collected, there were clouds out in the area and the temperature was not ideal to receive the maximum temperature gain that we needed to heat the coop to the specific temperature that we desired.
And the last question was, we have faced several difficulties. What difficulties you did not think before executing the project? What was the biggest difficulty? The biggest challenge that we faced while executing the project was ensuring that the pump had proper prime, and that would be the pump that circulates the water through the solar thermal system. That was an issue because with it traveling through a pressurized solar thermal panel, it was difficult to push the water through initially.